Now that we've dealt with exponential functions, we're going to look at something that's related called geometric sequences in 7.8. We're going to be able to write and use what we call recursive formulas for geometric sequences. We're also going to have some explicit formulas for that too. But when we refer to a geometric sequence, sales prices in that last problem that we kind of skipped over, that would form a geometric sequence. What a geometric sequence means is that the ratio of any term to its preceding term is a constant value. It's a lot like an exponential function. You're not using adding or subtracting, using multiplication to get from one number to the next. So in that geometric sequence, you're going to have a starting value, you can just call that A, and also a common ratio, which we're just going to call R. And again, it's a sequence of the form A times R squared, A times R to the third. You basically just keep multiplying by bigger and bigger powers of that common ratio. So first of all, we can come up with what we call a recursive definition for that sequence. And recursive definitions come in two parts. First, there's a separate equation that just states what's your first number. So if I say a sub 1, that's our first value in that sequence, and that's equal to whatever I see first as my first number. In the second part of our recursive definition, we're going to have a sub n, so that's referring to any nth value that you want to find in your sequence. We can find it by taking a sub n minus 1. And n minus 1 in this case would just mean the term that came right before it. We're going to take that term and we'll multiply it times r. And that's going to be, again, the rest of that sequence. We have a first value, and then we have basically an expression telling us where can I go past that first value. We're going to see that with some examples. Besides a recursive definition, we can also have an explicit definition, and that's always just going to be a single formula. We still have the same two pieces. We still have a starting value and a common ratio, but this time we put them both into the same equation. So in this case, a sub n is equal to that first term, a sub 1, times r raised to the n minus 1 power. So we still have a first term and a common ratio. In explicit formula, we just put them both into the same equation. And it looks a lot like an exponential function too. Kind of like our a times b to the x, what we used last time. So every geometric sequence is going to have two pieces, starting value and a common ratio. Starting value and the common ratio define a unique geometric sequence. So it does tell you kind of what your sequence is going to be as an equation. So if we're practicing that with a few sequences, which of the following are geometric, and if not geometric, is it arithmetic? And arithmetic we saw a while ago, but we're going to see that again on question B. It comes up. First, I made an adjustment to question A. It had a 16 written in there, but I just crossed that out and wrote a 6 instead. So if my sequence is 3, 6, 12, 24, and 48, we can tell that that's geometric because it does have a common ratio. As I'm going from one number to the next, every time I'm multiplying times 2. We can also think of that as 6 over 3, 12 over 6, 24 over 12, 48 over 24. If I took those as fractions to make my ratios, that's also simplifies to 2 over 1. 6 over 3 is 2 over 1, just like 12 over 6 also simplifies to 2 over 1. So that first case is geometric because we multiply to get our next term. In part B with that sequence, it looks like I'm always adding 3. 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. So that's an example of an arithmetic sequence. Arithmetic is kind of like your linear equations. If you're ever adding or subtracting the same amount every time, that would be an arithmetic pattern, but not geometric because we're not multiplying. On part C, even though we're using fractions, 1/3, 1/9, 1/27, 1/81, we are multiplying by the same amount every time. This time we're just multiplying times a fraction. That still makes that pattern geometric. Since I'm multiplying times 1 over 3, 1 over 3, 1 over 3, if I keep multiplying times a third, if that's how I get my next number, again, that would still be a geometric sequence since I'm using multiplication. And the last sequence for part D, it looks like we add 3 to go from 4 to 7, then I add 4 to get to 11, add 5, then add 6. That'd actually be neither. It's not arithmetic, even though I'm adding, because I'm not adding the same amount every time. I'd need to be something like adding 3 every time, adding 4 every time. I can't keep increasing the amount that I'm adding by. So that would be neither arithmetic nor geometric. I'm not multiplying, and we're also not adding the same amount every time. So also any geometric sequence, again, we see our two formulas can be written both explicit and recursive formula. Recursive formula is useful for finding the next term in a sequence. So that's if I start with a few values, I just want to extend that a few terms more. Explicit formula is better and more convenient if I just want to jump to a certain term. So if I ask for like the 100th term in a sequence, it's going to be easier to use that explicit formula. With recursive, you'd keep having to find each term until you get up to 100. So on a question like this, we're trying to find the recursive and explicit formulas for both of those sequences. We should be able to come up with, again, recursive and explicit formulas for each. The only two things that are important for both of those formulas, again, are a starting value and a common ratio. So looking at the first sequence, 2, 4, 8, 16, so on and so forth, the starting value would just be 2. That's just the very first number I see in that sequence. And the common ratio is also 2, because to go from one number to the next, I'm always multiplying times 2. So it's good to keep track of those two things first. If we remember back to our recursive formula, we have an equation that comes separate, which is just stating our first value. So if I'm making that recursive formula, all I have to say for our first equation is that the first term is equal to 2. That's just where our sequence starts. And then for the rest of that recursive formula, notice that this part's always going to be the same. You're always going to have a sub n equals a sub n minus 1. That's just describing wherever I want to get to with my nth term. I look at the one before it. So this is like saying my term is equal to the previous term. In this case, we're just multiplying times 2. So that part you're going to see is going to be the same on every recursive formula. You always start off by saying, okay, what term am I looking for? Which one came before it? I just got to take that number and multiply times 2. So if I have 16 and I want to get the one after that, take 16, multiply times 2, that's why I get 32. So it's pretty quick to find my next term. And again, that's following our formula. We have our first term, write that in a separate equation, and then our common ratio, we're just multiplying times whatever came before it. With explicit formula, it's the same idea. We're taking those same two pieces, a starting value and a common ratio. Now we just plug them into the same equation. With our explicit formula, it's kind of like your exponential form. We have our starting value first. Our sequence starts with a value of 2. It looks like every time we multiply by 2, so we put that number in parentheses. That's our common ratio that we're going to be raising to a power. And the only difference with our exponentials is that we use an x as an exponent. In this case, for our explicit formula, our exponent is just n minus 1. Since we should start our sequence with the first term and not at 0, like an exponential function, we're going to use 1 in that equation when we first start. So same kind of idea with our next pattern. If I start with 40, 20, 10, 5, so on. First two things I want to keep track of, just like the last question, is where our sequence starts and what our common ratio is. Sequence starts at 40, that's just our very first term, so I can make a note of that first. It looks like in this case we're dividing by 2. You don't want to list 2 though as your common ratio. You always want to think in terms of multiplication. So if we multiply in this pattern, that was multiplying times 1/2 or 0.5. You could use a fraction or a decimal, doesn't matter, as long as you use that common ratio as basically a half. So you just don't want to use a common ratio of 2. With our recursive formula, again, it's 2 equations. First one, just state where we start. We start with our first value at 40. And with the second equation of the recursive, again, this part's always the same. You're always going to have that beginning, a sub n equals a sub n minus 1. That just tells you, again, wherever I want to go, I look to the number that came before it. And in this case, I just multiply times 1/2. So that's our common ratio that we stick on to the end of that formula. And explicit, again, same two pieces, starting value and common ratio. Now we just use those in the same equation. So a sub n, I start at 40 on the outside. 1/2 is my factor. In this case, it's kind of like a decay factor. Keep multiplying times 1/2. And I raise that to, again, the n minus 1 as a power. And that's going to be consistent every time we use that explicit formula. Always going to have that n minus 1 for your exponent. So question 2 is also pretty similar, so let's see if we can run through these the same way. If we're trying to make a recursive and explicit formula for each sequence again, this time we just have one extra instruction, which is to find the 8th term. So just like our last couple questions, we want to keep track of, in this first sequence, where do we start? Looks like we start at 14 for our first value. And we can always use division. If I take 84 divided by 14, 504 divided by 84, 3024 divided by 504, if I take a number and divide by the one that came before it, we can see that the common ratio is 6. I multiply 6 every time I want to advance to the next number. So same two pieces, I just stick those into my formulas. Recursive, remember it's a separate equation first for your starting value. Our starting value is 14. And then from there, we start our recursive formula with our term is equal to the one that came before it times 6. So if that's our common ratio, we just throw on a times 6 at the end. Same idea with explicit. We have our starting value is 14. Common ratio is 6. Raise that to n minus 1 as an exponent. And that means if I'm looking for the 8th term, the explicit's going to be easier to work with. I don't have to keep finding like the 5th, 6th, 7th terms in order to find it. I can just jump straight to the 8th term using my explicit formula. Just means I got to substitute in 8 for n. So if I take 14 times 6 to the 8 minus 1 as a power, basically just raising that to 6 to the 7th power, if you end up multiplying times 14, should get almost about 4 million. So 3,919,104. Trying the same thing on the second sequence. Again, we've got to keep track of, first of all, where do I start? Looks like we start at 648. And what happens every time? Looks like these are being divided by 2. So again, you want to list that as multiplication. We're multiplying times a half or 0.5. So recursive, again, start with your first value. First term is 640. And then for every term after that, I look to the one that comes before it, and I multiply times 1/2. So again, that recursive formula is always going to be the same for that second piece. Explicit, same two pieces. We start at 648. We're multiplying times a half, and we raise that to the n minus 1 as an exponent. That matches our formula. And again, if I want to find the 8th term, that's easiest to do with explicit. Just take 8 and substitute it into your formula for n, and that should give you a value of about 5.1 if we're rounding that to the nearest tenth. So one last thing we're going to end with is we can represent a sequence by using function notation also. Allows you to plot the sequence using the points n and a sub n, where we start with the n as the term number and a sub n as the term itself. So it's kind of like looking at 1, 2, 3, 4 for term numbers, and your actual value would be the term. So let's say if we start a geometric sequence with an initial value of 2 and we use a common ratio of 3. Got to write that in function form. And it's a lot like your explicit formula. First thing, just like the last few questions, if we start with a first value of 2 and we use a common ratio of 3, I just got to follow my explicit formula to put that into a function. My a sub n, again, that's saying whatever term I'm looking for. I start with 2 as my starting value. I multiply by powers of 3 because that's my common ratio. And in that formula, we're going to use n minus 1 as an exponent. So the only change I would make to that, if we're going to put it in function notation, is we're just going to swap out, instead of talking about the sequence number, we're just going to say f of x. That's our function notation. Our function of x uses the same two parts. 2 is the value that we started with. 3 is the number that we're multiplying. And instead of n minus 1, we're just going to say x minus 1 because we're putting that, again, as a function of x. So if we want to graph this function as well, it tells us to graph it. Kind of like when we're graphing our exponential functions, it's going to be the same idea. I can start off with a table of my x and y values. Since we're making a sequence, it's going to make sense to start that sequence at 1, because that would be our first term. So if I use something like 1, 2, 3, I can substitute a few x values into my function and see what my y values are. If I substitute in 1, again, that would make an exponent of 0. Any exponent of 0 makes that entire second half 1. So again, that's just like saying when I start my sequence with a first term, that should be the starting value of 2. And then since my common ratio is 3, I could get the next parts of my table just by following that pattern. 2 times 3 would give me 6. 6 times 3 would give me 18. Could keep going on from that. So let's say if I want to go one more term, 18 times 3, that would give me a 54 for the fourth number. As long as I have my x and y table, we just want to fit that into our chart. And we should see that our exponential form is going to look a lot like your geometric sequence. So if I have a geometric sequence of numbers, since I keep multiplying by the same positive number, it's going to be positive 3. That's going to keep increasing as I go to the right. So make sure you have these notes completed and work on some practice with that in class.